Good morning. Today's video is about a trigonometric review, or at least what I use with my calculus students at the beginning of the year to prove and demonstrate techniques involving trigonometry. So the idea is to solve this here equation. None of the traditional techniques of squaring both sides yield any results. It's quite frankly an algebraic nightmare. So I use this as a way to introduce techniques to the students. And the first technique is a substitution method, a substitution technique that they rarely have seen in pre-calculus. So let's give it a try here and let x right here be equal to the cosine of an angle that I can call alpha. Okay. Why make this change of variable? Well, when I realize that whatever I have right here under the square root has to be positive, 1 minus x squared has to be positive. That means that x has to be between -1 and 1. Correct? Which tells me that maybe it can be related to some trigonometric function like sine, cosine, secant, or cosecant. Actually, no, not secant and cosecant, just sine and cosine that are between -1 and 1. And here I have 1 plus root x, so if this is between -1 and 1, then we're golden right here. This will be defined. Same thing here, if this is between -1 and 1, this will be great as well. So this here change of variable might make sense. Okay, will that yield results? We don't know yet, but we need to try things. Okay? So let's see what we can do here. Okay? Let's rewrite this, making that change of variable. That will become 5 times the square root of 1 plus cosine alpha plus the square root of 1 minus sine alpha equal 6 cosine alpha plus 8 times 1 minus cosine square alpha. Okay, so hopefully you see right away that this is equal to sine square alpha. Yep, it's called a Pythagorean identity. And this allows us to rewrite everything as 5 times the square root of 1 plus cosine alpha plus, this should be cosine, my apology, 1 minus cosine alpha equals 6 cosine alpha plus 8 sine alpha. Okay. So often at this point I have students who tell me, well, what if I don't remember this? Okay, no problem, let me show you where it comes from. If you take a unit circle, meaning a circle whose radius is equal to 1, okay, unit circle, the radius is equal to 1, r equal 1. If you take any angle, alpha, like this, okay, graphically, what is the definition of sine alpha? What is the definition of cosine alpha? And how is tangent alpha defined as well? Well, if I take the point of intersection right here of this ray with the circle, if I project this onto the horizontal axis, this gets me a distance right here. And this distance is equal to cosine alpha. If I consider now the projection of that same point onto the y-axis, then that projection is the sine of the angle alpha. You may still ask, why? Well, you know that by definition, cosine of an angle is the adjacent side over the hypotenuse, and that sine of an angle is the opposite side of over the hypotenuse. So if we're looking for the cosine of this angle, it's going to be the adjacent side of this right triangle over the hypotenuse, which is 1. Therefore, this is the cosine of the angle. This is its graphic representation. Okay? In this triangle, this is the opposite side. This is still the hypotenuse, equal to 1. But the opposite side right here is equal to this side right here, so we can say that this is sine alpha. Okay? And if I draw the line tangent to the circle at the point of coordinate 1, 0, then this height right here is going to be equal to tangent alpha. How do I know that? Well, I know that tangent alpha is equal to the opposite side over the adjacent side. Correct? But it's the same ratio as this side over this side. So this is tangent of the angle alpha. How does it relate to that? Well, let's go back to this little triangle here. Let's call it the triangle OAB. And let me redraw that triangle. The triangle OAB is a right triangle. This side right here is cosine alpha. This side right here is sine alpha. And this side right here is 1. It's part of the circle, so the hypotenuse is the radius, it's 1. We good? Now, we can apply the Pythagorean theorem to this, which gives us cosine alpha square plus sine alpha square equal 1. 1 square is equal to 1. So that gives us one of the Pythagorean identity. And if I manipulate this algebraically just a little tiny bit, I'm going to get up here 1 minus cosine square alpha equals sine square alpha. And then ultimately the square root of sine square alpha will be just sine alpha right here. Okay? Now you might ask yourself, okay, that's one of the Pythagorean identities. I remember having learned about 3 of them. How do I remember the other one? I don't have any other triangle right here. Correct? But you can use a little bit of algebraic manipulation. Pretend that you divide everything here by cosine square alpha. Cosine square alpha divided by cosine square alpha will be 1. Sine square alpha divided by cosine square alpha will be tangent square alpha. And cosine square alpha, once 1 is divided by it, gives us secant square alpha. So that gives us another Pythagorean identity. And for the third one, we just divide that first equation by sine square alpha. So cosine divided by sine is cotangent, so cotangent square alpha. Sine square divided by sine square is 1. And 1 divided by sine square is cosecant square alpha. And so now we have established our first set of results. These are the 3 Pythagorean identity. Okay? Let's go back to this equation right here. So we have 5 times the square root of 1 plus cosine alpha plus the square root of 1 minus cosine alpha equal 6 cosine alpha plus 8 sine alpha. So this is still not easy looking. But if you remember the double angle formula, maybe you can realize that there is something going on right here. Most of the time I have students who, since I start this at the beginning of the year, tells me I don't remember the double angle formula. So okay, then let's review the double angle formula and see what we can do besides that double angle formula with it. Okay, so at this point I introduce to them a technique developed by Euler involving trigonometry, exponents, complex numbers, a bunch of things. And essentially, I'm not going to prove it at this point. That's an interesting proof, but I'm not going to prove it at this point. I'm just going to share it with you. And e to the I theta will be equal to cosine theta plus I sine theta. Okay? So E, yes, it's Euler's number. It's 2.7182818828. I like to call it Andrew Jackson's number because Andrew Jackson was the second president, the seventh president. He served for 2 terms. So 2 terms, 0.7, he was the seventh president. And he was elected in 1828, so 2.71828. So this is I, the complex imaginary number, so defined as I squared equal -1. This is an angle, this is cosine of the angle, plus I sine of the angle. Okay? And once we have this notation, again, I'm just going to ask you to take it at face value for now. Here is what we can do with that. If we consider this here notation, so here we have the sum of 2 angles, okay? You see it's equivalent to the theta right here. Now this here, according to this definition, will be cosine of A plus B plus I sine of A plus B. But according to the rules involving exponent, this is also going to be e to the IA times e to the IB. And if I use the definition right here on this one and then on this one, it's going to give me cosine A plus I sine A times cosine B plus I sine B. At this point, I'm just going to distribute everything, and it's going to give me cosine A cosine B plus I square sine A sine B plus I sine A cosine B plus I sine B cosine A. Okay. Now we know that I square is equal to -1. So this will be cosine A cosine B minus sine A sine B plus, and at this point I'm going to factor the I right here. So I sine A cosine B plus sine B cosine A. Okay. What does that mean? That means that this here complex number is equal to this here complex number. And if 2 complex numbers are going to be equal to one another, it means that their real parts will be equal and their imaginary parts will be equal. Therefore, the real part is cosine of A plus B right here. The real part right here will be cosine A cosine B minus sine A sine B. And the imaginary part right here will be sine of A plus B equal sine A cosine B plus sine B cosine A. And once you have practiced this little proof, it's not that long, and it allows you not to make mistakes when you use the sum formulas for sine or cosine. Okay. If you wanted this difference formula, you can replace b by -b and use the fact that cosine b is equal to cosine of -b and that sine b is equal to negative sine -b. Okay. But here we have the sum formula for cosine and sine. So that's a different result. Now, the point was to find the double angle formula. Okay, so let's go about it. And the double angle formula is a formula we're going to get when A is equal to B. So if we say that A is equal to B is equal to alpha, then this here will be cosine 2 alpha, right, alpha plus alpha, equal cosine alpha, which is cosine square alpha, minus sine square alpha. And then if I use the Pythagorean identity that I just showed you earlier, you can say that cosine 2 alpha will be, instead of this, we can say 1 minus sine square alpha. So it's going to be 1 minus sine square alpha minus sine square alpha, 2 sine square alpha. Or we can say that cosine 2 alpha is equal to, we're going to replace this by 1 minus cosine, so it's going to be minus 1 minus cosine, so minus minus will be plus. So 2 cosine square alpha minus 1. So now we have the double angle formulas for cosine. And if I wanted the double angle formula for sine, I just replace A by alpha, B by alpha, and that gives me sine alpha cosine alpha plus sine alpha cosine alpha, which is 2 sine alpha cosine alpha. So at this point we have all the double angle formulas. And if you recall, we wanted to be able to use this in order to solve this. So I'm just going to concentrate on this part first, show you how to do it, and then this part second to demonstrate again. Okay? So let's do that right here. Square root of 1 minus plus cosine alpha. What is that equal to? Well, according to the double angle formula, we know that cosine 2 alpha is equal to 2 cosine square alpha minus 1. Which means that if I add 1 to both sides, I'm going to get cosine 2 alpha plus 1 is equal to 2 cosine square alpha. And if I take square root of both sides, it's going to give me the square root of 1 plus cosine 2 alpha is equal to root 2 times cosine alpha. I grant you that's going to be plus or minus that value, but we're going to leave it like this. You see, it will make no difference. Now, do we have the same thing right here? Almost, not quite. If we consider this angle alpha and this right here, 2 alpha, that might be an issue, right? So we could, instead of alpha right here, have a different angle. We can call it the angle theta, we can call it the angle theta. It's just a name. It doesn't really matter that much. Which means that right here we would have this, and right here we would have this. Right? Now we can make another change of variable. We can say that we're going to let 2 theta be equal to alpha, which means that theta is going to be equal to alpha over 2, divide both sides by 2, right? And if I now replace those two variables in here, that's going to give me the square root of 1 plus cosine alpha is equal to root 2 times cosine of alpha over 2. So I now have this original expression simplified, and it is simplified because now I don't have a square root anymore. That was really the pesky thing right here. Yep, so we're good. We're going to repeat this process with the square root of 1 minus cosine alpha. And instead of basing it on cosine 2 theta being equal to 2 cosine square theta minus 1, we're going to say it's equal to 1 minus 2 sine square theta. Okay? So I'm going to take this element, put it over here, take this element, put it over here. That's going to give me 2 sine square theta equal 1 minus cosine 2 theta. If I take the square root of both sides, it's going to give me root 2 times sine theta equal to square root of 1 minus cosine 2 theta. And if I make the same change of variable as this one, it's going to give me root 2 times sine alpha over 2 equal square root of 1 minus cosine alpha. So you see that a lot of the time is dedicated toward proving those formulas so that we can then use them. Right? So let's go over the left side of this here equation. So it was 5 times the square root of 1 plus cosine alpha plus the square root of 1 minus cosine alpha. Okay, it's just the left side of the equation. So if now I use the fact that this here term is equal to this, it's going to be root 2 times cosine of alpha over 2 plus root 2 times sine of alpha over 2. So it's going to be 5 root 2 times cosine of alpha over 2 plus sine of alpha over 2. And if you recall, this was equal to 6 cosine alpha plus 8 sine alpha. 6 cosine alpha plus 8 sine alpha. So is this equation really simpler than the original equation? Well, the issue that we had before was those square roots. We don't have any square roots here. So I would argue that yes, it is an easier looking equation right here. Okay. Now we have an half angle right here, we have an half angle, we have a full angle and a full angle right here. So we have things to do. Would you agree though that whether we're talking about the left side of this equation or the right side of the equation, this is in a form of A cosine alpha plus B sine alpha? That's the structure of this expression here. That's also the structure of this expression right here. Right? Okay. So at this point, I'm going to demonstrate how to address the techniques used to solve equations when you have a number right here that looks like this. Okay. So the idea is to try to relate A to the sine of an angle, and I'm going to call it the angle theta. So I want A to be related to the sine of this angle, and I want B to be related to the cosine of that same angle. Okay. Now, there is no guarantee that A is a number between 0 and 1. There is no guarantee that B is a number between 0 and 1. So I cannot directly say that this is equal to this is equal to this. Hence the word related. But let's pretend that I have related this coefficient to the sine of an angle and this coefficient to the cosine of an angle. That will allow me to rewrite this as sine theta cosine alpha plus cosine theta sine alpha. And if you recall the formulas that I have shown you earlier, this one right here, we can say that, sorry, this one right here, we can say that this here will be the sine of alpha plus theta, making everything even simpler. Okay? So, how do we relate that? It's actually quite simple. If we take a right triangle right here, and we say we have an angle theta, If sine theta is related to A, we can say it's going to be related to this side right here. And if this is related to cosine theta, we can say that this will be B right here. Okay. And if we have an A right here and a B right here, that means that according to the Pythagorean theorem, the hypotenuse will be the square root of A squared plus B squared. Which means that the sine of the angle theta would be equal to A over the square root of A squared plus B squared. And the cosine of the same angle will be equal to B over the square root of A squared plus B squared. Right? So let me demonstrate how this can be used with this here first equation. So let me rewrite it. 6 cosine alpha plus 8 sine alpha equal. So this will be my A. This will be my B. Right? A, B. So A squared will be 36, B squared will be 64. 36 plus 64 is 100. Square root of 100 is 10. Right? So what are we going to have here? I'm going to essentially divide by 10. So I'm going to have 6 divided by 10 times cosine alpha plus 8 divided by 10 times sine alpha. Now careful, a lot of students make the mistake. You cannot say that this is equal to this when you divide by 10. If you want to say they are equal, you need to also multiply by 10 like this. Okay? So, how does that help? Well, we can say at this point that there is going to be an angle theta defined by saying that sine of theta is equal to 6 over 10 or 3 over 5, and that the cosine of that same angle will be equal to 8 over 10 or 4 over 5. Okay? So this angle theta is defined now, which then allows us to rewrite the fact that this here expression is equal to 10. So remember, sine theta cosine alpha plus cosine theta sine alpha is equal to sine of alpha plus theta. Do I know what theta is equal to? No, not really, but it is defined completely, right? And if I wanted to know theta, I could plug it in my calculator. Okay? So this result is 6 cosine alpha plus 8 sine alpha is equal to 10 of sine of alpha plus theta. Okay? That is for the right side here of this equation. I'm going to do this again with this side right here. I'm going to leave the 5 root 2 out for the time being. I'm just going to concentrate on this. Okay? So we're going to have cosine of alpha over 2 plus sine of alpha over 2. Okay? So the coefficient A is 1, the coefficient B is 1. So I'm going to divide 1 by root 2, 1 by root 2. So that's going to give me root 2 over 2 cosine alpha over 2 plus root 2 over 2 sine of alpha over 2. And I need to multiply everything by root 2 right here. And now those two sides are equal. Okay? Now you might recognize that if this is the sine of an angle and this is the cosine of the angle, you can say that the angle is pi over 4. So you could rewrite this as root 2 times sine pi over 4 cosine alpha over 2 plus cosine pi over 4 sine alpha over 2. And it's equal to root 2 times sine of alpha over 2 plus pi over 4. Right? So if now I write the equation 5 root 2 times cosine alpha over 2 plus sine alpha over 2. That's going to be 5 root 2 times this, which will be 10, times sine of alpha over 2 plus pi over 4. So that was the left side of the original equation. Let's rewrite it here. We're going to have 10 times sine of alpha over 2 plus pi over 4 equal, and if you recall, it was equal to, right here, 10 sine of alpha plus theta. 10 sine of alpha plus theta. Okay, it's looking pretty good. Look, we have 10 right here and 10 right here. We can divide both sides by 10. We have alpha over 2 plus pi over 4. We have alpha plus theta. Okay. If I apply the arcsine function to both sides, it's going to give me alpha over 2 plus pi over 4 equal alpha plus theta. And if I subtract alpha over 2 from both sides, it's going to give me alpha over 2 equal pi over 4 minus theta. Right? Alpha minus alpha over 2 is alpha over 2. And put this over there, so pi over 4 minus theta. Which means that if I want alpha, multiply both sides by 2, it's going to be pi over 2 minus 2 theta. We good? All right. Pause the video at any time if you need some time. Work it out, and it's good. Now, we don't want to solve the equation for alpha, though. We wanted to solve the equation for x. And remember that x was defined originally as cosine alpha. That means that x is going to be equal to cosine of pi over 2 minus 2 theta. Let me rewrite the formula one more time. For cosine of a plus b. Remember that cosine of a plus b was equal to cosine A cosine B minus sine A sine B. Which also means that cosine of A minus B was cosine A cosine B plus sine A sine B. So if I apply this formula to this, that will give me cosine pi over 2 times cosine 2 theta plus sine pi over 2 sine 2 theta. Right? If you know your trigonometric value, cosine pi over 2 is equal to 0, and sine pi over 2 is equal to 1. That means that this is gone, and we are left with x equal sine 2 theta. So I'm going to rewrite it. X is equal to sine of 2 theta. We already reviewed the double angle formula. That's equal to 2 sine theta cosine theta. And if you recall, sine theta and cosine theta were completely defined at the beginning of the problem right here. Sine theta was 3 over 5, cosine theta was 4 over 5. So you're going to be having 2 times 3 over 5 times 4 over 5. 2 times 3 times 4 is 24. 5 times 5 is 25. And it's equal to 24 over 25. Plug it in the original equation and you will see that it works out beautifully. Don't forget to work with love. All right, I hope it was helpful. Good luck.